So, hi everyone. My name is Aryan Jogia. Today, me with my co-speaker Chetanya Kunndra will be presenting a session titled "Playing the Game of Tag with Modern Day AV and EDR." Let's start with the introduction. Again, my name is Aryan Jogia. I'm a security researcher with four plus of years of experience in the domain of Windows system level programming, and I also hold a certification of CRT. Pass on to Chetanya.
Yeah, hi, I'm Chetanya Kunndra, 3+ years of experience as security researcher, and I'm currently the team lead at my organization. And I'm also CRT certified. So, with that, let's start with the presentation itself. I'm pretty sure everyone, or majority of you know what exactly are AV and EDRs, but still, let's roll over some basic concepts before we start diving into the field of antivirus evasion and EDR evasion. So, an antivirus software basically is any sort of security solution that protects a system against known threats. They're designed to scan web pages, your applications that are dropped onto the system. You're downloading something from the internet. They scan that against known signatures, and they verify or they check whether or not that particular file is a malicious file or it's a benign file. So based on that sort of deductions, they delete the file and sort of protect your system from any sort of infection. On the other hand, EDR or endpoint detection and response, they're essentially they used to manage your network. So let's just suppose you have thousands or even hundreds of systems in your network. They used to monitor the ETS and ingress traffic of the particular of all the systems in the network, and they analyze other system level events present in each of the systems to, and then they use various data analytics technique, machine learning techniques to identify whether or not a particular behavior is malicious or not. So the key functions of EDR are endpoint data monitoring, automated remediation, investigation and learning, isolation of affected partitions, and alerting your soft teams as and when necessary. So it is important to understand the difference between an antivirus and an EDR. An EDR works on the entirety of the system. They collect all your egress and ingress traffic, your system level events, and various other parameters of the system. However, antivirus solely is responsible for analyzing and detecting your files that are dropped onto the system or the commands that you are executing. So there is a key difference between both of them. So, before we bypass any sort of malware or before any malware developer bypasses any AV or EDR, there's certain prerequisites that we need to understand. So, in this sort of section, we understand what's user in kernel mode within Windows. I'm not really sure what's the level of understanding of the audience here, but we'll still give a brief overview of the user mode, kernel mode, and Windows API, brief overview of the Windows API because Windows API has a key components when developing Windows applications, be it useful or be it harmful. Then we will also various different detection methodologies implemented by AV and EDRs, followed by Hackin, which is exactly how AV and EDR security solutions collect your data. So the Windows ecosystem. Within the Windows OS architecture, there are two different privilege levels. So these privilege levels that isolate the Windows kernel from installed applications. So this bifurcation is important because this helps the Windows kernel from crashing due to an unstable application. For example, let's say a notepad crashes. So if a notepad crashes, you can restart a notepad.exe from your system, but your Windows OS will remain as it is. It won't harm your Windows OS. So in any modern day of operating system, whatever virtual memory we have, it is divided into two memory spaces or two separate regions for our OS to use and for the user mode applications to use. These two address spaces are called the user space and kernel space. So the importance of these user space and kernel space is that it defines where our AV and EDR components can actually analyze what's going on in the system. So all the applications that are running on your Windows operating system right now, let's say for example the Zoom client or whatever, let's say suppose this presentation, the Chrome browser that I'm running the presentation on is running in the user mode or in the user memory of the user memory section of the memory. All the kernel and device drivers are running in the so-called kernel mode or in the kernel space of the memory. So each of these two spaces are separate from each other and they have their own memory space. Neither of the two can directly manipulate each other. So in 2005, I believe, Windows came up with kernel patch protection. Kernel patch protection ensured that no application in the user land can monitor or sort of patch the kernel memory space. This ensured that AV and EDR systems can only monitor applications that are running in the user space. So if everyone must be aware of the CrowdStrike Falcon BSOD crashes. So due to their driver itself, they were patching into the kernel Windows OS kernel. That's why due to the faulty patches, the Windows OS crashed. So this is one of the prime examples where Windows introduced kernel patch protection. So during a normal run, the actually code flow it moves from the user mode to the kernel mode via the NTDL. So whatever API functions we are calling go to APIs or functions that are already defined within the NTDL file, and after that the CPU switches to kernel mode, and that after that point no API APIs can monitor what's sort of going on or what sort of APIs are being called. So this here right here is this is the Linux user mode and kernel mode diagram that explains what sort of applications are running in each of the user mode and kernel mode. So as we can see that in user mode we have a C standard libraries, the Windows Manager, system variants and all that. And in kernel mode we have our memory management subsystems or virtual files or process scheduling subsystems. Although it's for the Linux, this is also valid for the Windows environment as well. So let's understand what exactly are Windows APIs. Not everyone in the cybersecurity domain interacts with the Windows APIs, window APIs or many APIs, as we popularly call them. Primarily because coding is a bit difficult for these. You need to understand a lot of data structures and all the integrations and all. But Windows specifically has provided developers or other sort of software companies or to us in general, Windows APIs, which are a set of functions or that are predefined that we can use to access base services of Windows, such as the file system, the process, and threads. This right given below is the create file API, which is the most popular kind of API being used in legitimate and malicious applications as well. This create file API is responsible for reading and writing files and input-output descriptors. Now, why exactly do we use Windows API? Windows APIs are used because they are very efficient and they sort of optimize by Windows to interact with the Windows kernel. So it allows us to create applications without any sort of worrying about what sort of kernel components or what should be the state of the kernel when we call we sort of interact with the different component. So Windows API provides us with predefined rules or predefined functions that we can directly use without any worry whatsoever. So right here below, I just like I previously told you that create file A, it's just open files and I input output devices for reading and writing. Similarly, there's another API called Flash Window X that lets us change the title bar from light and dark shades. So this, apart from these, there are a lot of Windows APIs that we can use or that are generally used by malware developers. So on to the detection techniques. So most AV and EDR solutions generally implement three major type of detection techniques. First is a signature-based detection technique. AV compares files that are present on the system against known malware signatures. So for this detection technique to work, the AV database must stay up to date with the latest malware signatures at all times. Second is the heuristic-based detection. Heuristic detection looks for similar tendencies between files and between processes that are executing on the network. They are able to catch your malwares or your malicious intent that are not detected by a signature-based detection. And your third last detection third or last detection category is a behavior-based detection. This form of detection examines how a file or program interacts with the memory or with the file system itself, and it sort of kills or stops anything from execution that is out of the ordinary. So within these three detection techniques, signature-based and heuristic-based detection techniques are also form of a we can also call them static detection. And similarly, heuristic and behavior-based detection can also be used in dynamic detection, or we can also call them dynamic detection techniques. So, to give you an example of signature-based detection, this right here is the YARA route to detect juicy potato. Juicy potato is a very popularly used previous escalation technique, or previous escalation tool. I'm sorry. So this right here, this rule explains what sort of strings are present within the juicy potato EXE. If you can see the string section here, if the author is sort of defining four strings, and in the condition section, he's saying that either of these four strings, if three of these four strings are present in the EXE, then there is a high possibility that the particular EXE is a sample of juicy potato. Onto how EDR works. So an antivirus similarly scans just for files or memory regions or data that's present on the system. They do not verify the data that is going from the system or that's coming to the system in sort of the network connections that they're making. And EDR, on the other hand, bridges that gap and sort of provides you a bird's-eye overview of what's going on in your network. And it provides comprehensive real-time threat intelligence and visibility. So, how exactly they work? There were 6 steps. They continuously monitor all the egress and ingress traffic that is coming from an endpoint. They also they also take event level data, Windows events level data from your system, and they use it to determine whether or not certain malicious activity has been performed on a system. So EDR also employ actively machine learning techniques and artificial intelligence techniques to identify anomalies that are present if within system that for here we define anomalies such as that are not triggered by our standard signature based detections. So those sort of anomalies are present there. And EDR, if triggered correctly, can also block certain IOCs from execution. And EDR solutions, they also give you the capability to cordon off certain infected components within your network. So let's say suppose system A within your network is compromised. It's an EDR solution identifies that system A is compromised. It will cordon off it from the entire network, preventing any sort of malicious actor from jumping to system B or system C from system A. Similarly, EDR solution also again employs machine learning and artificial intelligence technologies to continuously learn information about your system and about your network, and to identify whether or not certain things that are happening are anomalies or not. They can also alert your soft keys depending upon the severity of the alert. So on to Aryan, who will now explain how AV and EDRs collect information from the system.
Okay. Thank you, Chetanya. And so now we know like how India and AV works. So let's go a little bit deeper into the detection mechanism of the AV and EDRs. Hooking. So what is hooking? Hooking is a technique used to modify or the intercept the behavior of the program or a process or any of the program in the operating system. So actually, what does hooking or hooks allow? Like works in case of AV and EDRs. Hooks allow us to redirect the execution flow of a code to the trampoline function of the AV and EDRs. So it helps us to detect, it helps AV and EDRs to detect the malware. So it is of two types, like hooking is of two types, import address table hooking and the inline hooking. We'll be discussing this in the next slide. So import address table hooking, IIT hooking. What is IIT? IIT is like a contain the list of all the required DLL or the specific DLL needed by the EXE in order to execute. So these contains also, since executable needs to dynamically locate these specific DLLs or the required DLLs. So for that IIT is included into the EXE. Next. So as I've said that IIT lists all the required DLL files of the specific function or the import of from them. So IIT can be used by the AV and EDRs also. Since AV and the AV and EDRs can hook these particularly pointers, change the particularly pointers in order to get executed by the in order to pass on the execution to their temporary function. For that, like for these temporary function can detect the malware or inspect the parameters of all the APIs. Here comes the inline hooking. Second, inline hooking is similar to the IIT hooking. Inline hooking, like in the inline hooking, we just don't touch the executable. We just like AV and EDR can hook the NTDLL or the all the required DLLs needed to execute needed for the execution of the EXE. For example, kernel32.dll or the NTDLL or the WS2.dll. These DLL can use for the hooking by the most of the AV and EDRs. Like since the new generation AV and EDR use these techniques for the hooking for mostly detecting the malwares. Next. So since you know the mechanism of the detection mechanism, so these are the techniques we are going to discuss in this techniques. All the techniques are like, since there is a time constraint, we can't cover all the techniques briefly, but we'll try to explain these techniques in a concise manner. Next. Pass on to the Chetanya. These technique will be explained by the Chetanya.
So, okay, full disclosure before we start. This entire presentation was made sort of a training where we could, lightly code all these techniques and implement them when we're live. But due to time constraints and the format constraints, we'll briefly discuss what sort of techniques are being used by malware developers to evade antivirus and EDR solution. So, obfuscation and encryption. Obfuscation and encryptions are popularly used techniques. So these two techniques are primarily used to sort of bypass static-based detection. In obfuscation, what we do is simply we change the format or how a program looks. We do not tinker with what the program functions or how the program functions. There are various types of obfuscation techniques. Some sort of add benign code onto your network or to your code so that the code flow changes. Some change your function name, some changes your variables name. All that is done to ensure that the signatures of the EHC or the malicious payload do not match. Or if someone is analyzing from the blue key, they're not able to easily identify what's the nature of the malicious code or the payload. So if you see the image below, here's an unobfuscated partial script. So it's simply creating a TCP client and connecting it to a remote host. So if we look at it, if you look at it simply, it will be easy for us to identify, okay, it's making a connection, TCP-based connection. And these are the variables that are used. It's easy for us to understand, or any linking professional who is looking at it. So here's the unobfuscated version of that same script. Here the variable names have been changed to really long numbers. So this sort of renaming the variables will ensure that no signature-based detection occurs for this particular script. Although it's a very rudimentary example, but obfuscation can happen are used using LLVM or they're used widely. So the second technique to bypass string-based detection or static detection is encryption. So in encryption, what we exactly do is we encrypt our payload or our malicious payload. We encrypt it so that even if we keep it on the disk, it's sort of undetectable by any engine, or it's sort of it does do not match any sort of um, strings or any sort of uh, any sort of the rules, AR rules to be specific. So for the two major type of cryptors or encryptors as we call them, scan time cryptors, they decrypt the payload at runtime. When we execute those cryptors, they decrypt the payload and they drop it onto the disk and execute it. The issue with these cryptors is that when we drop it onto the disk, the payload itself should be undetectable by the AV engine or the client. Otherwise, there's no benefit of using this sort of crypto, because as soon as we decrypt the payload and you drop it onto the disk, the AV engine or the EDR engine will detect it and delete it. The second are the runtime cryptors. Runtime cryptors use various process injection techniques to decrypt the payload and execute it in memory, all during runtime. And this technique, the payload itself does not touch the disk. So there's no sort of detection when the AV or the EDR engines scans the disk. However, the payload itself can be scanned in memory by certain vendors, not all, but certain vendors. So on to our next technique, API hashing. So APIs, as we previously discussed, that Windows APIs are majorly used by all legitimate and malicious applications, and all applications that are designed to interact with Windows will use APIs for sure. So it is also possible for our threat researchers and UB specialists to understand what sort of the activity is being performed by an EHC, just by understanding what sort of APIs are being imported by the EHC. We discussed import address table briefly before. Import address table ensure kind of is a record of all the APIs that are imported by an EHC. So in the image on the right hand side, we can see that this particular EHC from the kernel 32 DLL library imports all these APIs that are shown below. Copy file W, compare string W, and close sample. All these APIs are being imported by this particular application. So by analyzing all these imports, we can get a fair idea of what this particular API might or what this particular EHC might do. For example, if we see that there is wrench create key X API being imported, we can assume that this particular malware or this particular application is creating a new registry entry, and this sort of understanding can help blue team specialists or EDR solutions or even threat researchers to look or hunt for the specific registry that is being created. And if let's suppose WS2_32.DRM is being imported, then we can safely assume that okay, this malware, this EHC has some sort of networking capabilities embedded into the code. So just like I said, that these APIs that are being used or being imported by EHC can be used to create indicators of compromise. Now, this is the issue for malware developers. So if you're using your APIs, let's say, if you look at the image on the right hand side, you can see that this particular ARL rule is used to detect remote code execution, remote process injection. And here he's stating all the APIs, or he's depending on the APIs that are generally used for injecting into a remote process. So if as malware developers, we are building an exploit or building a code that injects into the memory of another process. If we use these APIs openly, it will be easy for AV or EDR solutions to identify our intent and kind of block it before we even do anything. So in order to resolve this issue, or in order to prevent any sort of trace being left on the IAT, there is a technique that we can implement called API hashing. So API hashing ensures that no signature or no API that is being used by us comes or shows up on the IAT. So I'll be honest, in order to perform API hashing, we need to pass the portable executable format of Windows. So API hashing itself is a very long topic, and the code and the basic fundamentals of it are a bit complex for us to give it in this time frame. So we very briefly explain what's the process of API hashing. So there are very two critical components for implementing API hashing. One is a hash function and one is a resolver function. The hash function's sole task is to take a string input and give us a static or a hashed value for that particular string input. We can either rely on popular hashing algorithms like MD5, or we can create our own by XORing with a static key. That's entirely up to us. The resolver function, on the other hand, takes an API or a library hash that is returned by the hash function and searches who or P or the library that we are importing or that we want to import, looks for the function within its export directory and returns us the address of that particular function. Then we can use that particular address to invoke that function during runtime. So in this entire process, if we implement it with proper care and everything, it will ensure that there is no sort of trace present on our IIT. So here we have created a small code on the left hand side. If you can see, there is a small bit of code which is using the create process API to spawn a CND shell. This is a very benign example. This won't be detected by any AV or EDR engine, but just to give you an example, how API hashing will work. So on the left hand side, we have used our create process API. And on the right hand side, we can see that within, if we analyze this particular EXE, compiled EXE with CFF Explorer, we can see that create process W API is being imported. So if I'm a threat researcher, I can assume that, okay, this particular function or this particular this particular EXE is spawning a process that I can look for. So after hashing, what we have done here is if you see on the left hand side, the left image, we have we have defined a function that returns us the address of the hash itself. When we have passed this particular 0x hash, that is of the create process API itself. So what this particular function will do, it will import kernel 32 into the memory, and it will pass that kernel 32 in memory and look for the create process API within its code directory. So after we have the function address of the create process API, we typecast it into the standard defined by Microsoft, so that we know or the compiler knows what sort of arguments it will receive. So we typecast it into the create process that we've already created, and then we call it simply just by using create process or how we normally call a function. We call it just by the same by passing in the same parameters as we passed earlier. But the difference here will be after we have compiled it, and again, if we analyze it, we can see on the right hand side of the image that now there is no create process API that is being mentioned in the IIT of the EXE. It's using load library A to load kernel 32.DLL into the memory. We can also get rid of that by parsing the thread environment block or the process environment block during runtime to get the address of kernel 32.DLL itself. So API hashing is usually used to hide the intent of the EXE itself. It can also be used to bypass certain string-based detections, like on those rules that I usually told you. So now we move on to the anti-malware scanner interface. So in 2015, Microsoft introduced anti-malware scanner interface, or AMSI as it's popularly known, as a first line of defense to prevent any sort of execution by malwares. So AMSI is a very versatile tool that was developed by Microsoft. What AMSI does is it integrates itself into the partial memory space. It's primarily used with partial, it does not come with CMD, or at least I have not seen it in in real life. So what AMSI does is AMSI loads itself using the AMSI.dll library into the partial memory. So whatever input that is given to the partial, be it a string, be it a file that you are executing, it is sent to ASI, which is then sent to a antivirus solution. By default, then it's Windows Defender on most of the Windows OS systems, or it can be any other AV program that's pre-installed on your system. So there's no bifurcation whether or not it will open Defender only or itself. It will open any AV program that's installed. So it is scanned by that particular AV program, and if it's malicious, it will block the execution of that particular exe or the command itself. So also AVSI does not differentiate with whether I'm a low privilege user or whether I have a NT40 system shell or a high privilege console. Here in the image, if you can see, I'm just simply typed invoke Mimikatz. Mimikatz is a popular credential dumping tool. So it just states the string and it analyzes the string and it sees that okay, Mimikatz is being called. So it is malicious and it's breaking some sort of rules within our Windows Defender database, and it's blocking that particular execution of the script. Here we can see that it states that this script contains malicious content and can't be blocked by your antivirus software. So this is how AMSI works in real life. AMSI can be bypassed by using in-memory patching, and it is actively used by threat actors and malware developers. They use it to bypass AMSI during runtime by using memory patching so that they can execute any sort of partial commands on a particular system. So by using AMSI, by patching AMSI API, we can patch AMSI for the entire partial session. So if we see that, if we analyze AMSI.DLL, IDA or in Kunndra, we see that there are two primary functions that are being exported. First is the AMSI scan buffer and your AMSI scan string. These two APIs are responsible for detection of malicious input, be it your strings, be it your any sort of API or any sort of script that is being passed. So by analyzing these two APIs, we can sort of figure out what it's doing. On the right hand side, we can see that it's a decompiled code of AMSI scan buffer. Here we can see that a lot of checks are being performed. And after each of these checks verify, the input is sent to your AV or EDR vendor, and then it's analyzed, and depending on that result, the execution is logged or it's allowed. So, if we see AMSI scan string as well, what AMSI scan string does is it takes string input and it calls AMSI scan buffer in the background. So if we patch AMSI scan buffer in memory, we patch both these APIs and we don't need to specifically patch AMSI scan string. So the basic steps to bypass AMSI.DLL in memory are, we'll first load AMSI.DLL into the processor's memory, and then we'll scan or we'll fetch the address of the AMSI scan buffer API. We'll fetch the address of it, then we'll overwrite some specific jump instructions. Now these particular jump instructions will ensure that whatever checks are being performed, they always return this AMSI underscore result underscore clean result. So if we receive that result, we can safely say that okay, every form of command or every string that is being passed is it's not malicious, it's benign, it's completely fine to execute on the process itself. So we'll override certain specific jump instruction. After overriding these jump instructions, we close the handles. So here is a simple code that can be used to patch your AMSI scan buffer API. So first we load the AMSI.DLL into the memory using the load library API, and using get prop address, we can use AMSI scan buffer to get the address of the AMSI scan buffer API, and then we'll sort of change the predictions that are implemented by Windows or on the memory space of this particular function, and then we'll change or then we'll override specific offset. Here in this case, is 0x83. We override it by the 74 hexadecimal value, and then we'll again we sort of revert back to the old prediction that was implemented on that PLD space, and then we'll simply return. We close all the handles, and that's it. This is what's required to patch ASI scan buffer repair in memory. Here, the detections can be made detections can be made for this particular code if we put detections on MSI scan buffer, load library, and get from address strings. But these can also be bypassed using API hashing as we previously discussed, and by also sort of breaking up the strings. So on to Aryan will now explain ETW patching and the remaining of the techniques.
So ETW patching. ETW stands for event tracing for Windows. You must have all gone through the event here in your system. That is the events registered by the ETW itself. So ETW provides the mechanism to trace or log events. These events can be used by the AV and EDRs in order as a telemetry or in order to detect the malware or another samples. So ETW patching, but the patching of ETW will help us in being invisible to the EDRs or AVs or the guy sitting at the monitoring table of this org team. So, like if we see these screenshots of the NTDLL below the screen, so you can find there two APIs, ETW event write and ETW event write full. These are the APIs used for the registering the event into the event view. Right. So after further analysis, we found out that both of these APIs at last called the anti-trace event API, which is the API in the last level of the NTDLL. So if we patch this particular API, we can patch the whole ETW. So this is the simple code for the patching ETW. So what we get is that we found the address of the anti-trace event API from the NTDLL.dll and finding the address was using the getproc address. So what we found, we just write down the return instruction instead of their address using the memcopy and then finding when all the closing the handle and changing its permission to the normal permission and just that's it. But there is a note for this particularly ETW patching, which is that this patching can affect whole system wide. This patching will be a system wide patching. And there will be no system event registered after the patching. So another method is the Block-DLL. Block-DLL is the famous technique used by most of the malware or famous ransomwares also. So like we can bypass the AVs other than Microsoft Defender. Since Block-DLL method is a technique which prevents the third-party DLLs. By the third party, I mean the non-Microsoft signed binaries to get injected into your nitty or something. So this technique can be used by neither of the ransomware or all the malwares in order to prevent their AV and EDR DLLs to get injected while they are executable needs to run at the runtime. So, Block-DLL technique can be implemented using two APIs, update proc thread execute API and the set process mitigation APIs. Both of these APIs generally set the mitigation policy into the windows, which allows only Microsoft signed binary to be gets loaded during the runtime of the AHC. So like this is the diagram. You can see that AV and EDR launches a DLL and the program is running. So whenever the program executable executes, AV injects their DLL into that particularly AHC or in the memory, and then checks all the parameters of the API or all the other things what the program is doing. So this technique prevents the DLL of the AV and EDR to get loaded into our AHC. API unhooking. So unhooking, as the name suggests, unhooking is the removing all the hooks. As we know what our hooks are, so it's a simple method that attacker can use to load an unhooked version of hook DLL. So what we can do, unhooking can be done in two ways. Like, for example, we can unhook the full NTDLL or the DLL which is being loaded by the REXE, or we can just patch the particularly API which is being hooked by the AV or EDR. So this technique can be used in multiple ways. Although, for example, now in the first method, we can just read the .text section of the DLL from the disk and just put it on the top of the .text section of the DLL being loaded in the memory. So this is the technique. A second is the patching of the particularly API. For example, if our code is using a create process API and it is being hooked by the AVR or EDR, so what we do, we'll find the particularly instruction of create process API into the NTDLL into the disk from the disk, and we'll patch that particularly instruction to the normal or to the text section of the DLL being loaded by the malware. Next. So this is the repatching, which is the second method I have already explained. This technique is already discussed, like implemented in the further technique, like we have discussed all the ETW and the AMSI patching. This is the repatching techniques. Like we have patched the particularly API, not the whole DLL. That's the patch. This was the technique was firstly introduced by the MPSec in the beginning of 2019, and here's the blog. You can refer to it. Next slide. You can see the code into the given slide. This code refers to the is used to remove the silence hook for the DLL export. So if you see like in the particularly API name, you can get the for the like if you want to change the patch the particularly API, you can get the API name and get it address using network address. Then then get the permission using virtual protect and just patch the particularly address which you get from the DLL into the disk. And then again close the old handle. That's it. You have patched the particularly API and all the hooks are patched. Next. Direct system calls. So since Chetanya has already discussed the user mode and kernel mode, so since you all know that our OS are being developed into the ring structure, all the user mode applications are run into the user mode, that is ring 3 in this case, in this given structure, and all the kernel mode drivers, all the device drivers run in the kernel mode. For the this ring structure enables for the critical memory sections. Like if the user mode application presses, it won't affect the kernel mode. So as we also know, the last level of the user mode is the NTDLL.DLL. So for this, if a program needs to register or perform a privileged task, which needs a particularly privilege, so it has to switch in from the user mode to the kernel mode, and that's where the syscall comes into the play. Syscalls are the numbers, that is the CPU instruction that switches between the user mode to the kernel mode. If you see the particularly code or the diagram, so it will affect that move EX, 8. So 8 is the particularly syscall number that is used for the NT-write file. So this is the syscall number for the NT-write file instruction. Next. All the syscalls and the syscall numbers are associated with the APIs. Like all the APIs have their particularly syscall numbers. So there is one limitation for the syscalls also. Like these syscall numbers changes within the version of Windows. Even sometimes between the block or the product build numbers also. So these mapping of the syscall with the API are done into the are implemented into the SSDT table. SSDT is the system service descriptor table, which includes all the number and which maps all the syscall numbers to their particularly APIs. Since you already know that you can refer to the particular diagram. Application runs in the user mode, and all the hooks are placed into the user modes. All the AV ADRs are into the user mode. So all the application, they paste their books onto the particularly shared view, or we can say that the kernel 32.dll or the anti-DLL in this case of the diagram. So when we switches to the user mode, from the user mode to the kernel mode, there is no hooks or no AV. So why don't we use the syscalls, direct syscalls? So in order to bypass the AV here, yes, we can use the direct syscalls. Next. So since like I've only told the limitation of the syscalls, since it is a very vast topics, we can't implement or we can't show it here, but we can definitely use it. We can like you can execute this, that you can definitely use the direct syscalls numbers, or you can directly invoke the syscalls and leaving the user mode to the kernel mode in order to bypass all the hooks placed by the AV or EDR. There's one, I've already given one side program for the system number changes between the OS and version and central even. Fortunately, Google Project Zero come to the rescue for this limitation as their online system called tables. They have mentioned all the like they mentioned all the system numbers according to their versions. You can just refer to their blog or some or this link, or you can refer to our references. We are mentioned in there also. So they mapped all this response according to the Windows version. We can use the direct syscalls in the Visual Studio. Like it supports the .asm file. We can then invoke the syscall numbers as we can see the code and the diagram. So here's the we are using the particularly syscalls. It is the ASM code which we can use as a in the Visual Code, Visual Studio. So here comes the conclusion. Since there are multiple techniques and we can't cover it in here due to the time constraint, also there are multiple techniques and no single trick can do the magic. There always are multiple, there combination of techniques. So in order to bypass, so you have to just test and check, test and check, and then repeat the process. These techniques has also its own advantage and the limitations. So one should keep this the all the pros and cons of the techniques before using it. So these technique can be used by various malwares also in order to bypass the uh, AV and EDRs. We can move to the proof of concepts. Here's you can all have a look on it. Thanks, Adam. So, in this particular proof of concept, what we have done is we have used juicy potato that we have early discussed, and we have sort of run it as it comes onto the system, and then we have used various techniques that we've discussed in this presentation to make sure that an updated version of Windows Defender does not detect it. So, have a look at it, look at this particular POC.
that's it for the POC. Here are the references that we use for creating this presentation. We can definitely send it to you over Discord, or I think Ryan has already sent this particular presentation on Discord. So thanks a lot. That's it from our side.